Hey, good morning. Somewhere in the US, and then yeah, good evening and hi. Thanks for joining us. We have this will be our last webinar for a while, and then we will resume this webinar. This fall, and for now, it'll be our last. So, for today's seminar, we have Andrea Cremaschi from Singapore Institute for Clinical Sciences, and I mean, it's very late night in where he is now, but thankfully, he accepted our invitation, and thank you so much, Andrea. And he's going to talk about the repulsion, chaos, and equilibrium in mixture models. And Andrea, the floor is yours.
Thank you. Okay, let me share the screen. Okay. Thank you. Thank you for the invitation. Thank you for adjusting the time also. I think it's much worse for your morning than here. Here it's just 9 p.m., so it's still manageable. So yeah, my name is Andrea Cremaschi. I'm a researcher at A-Star and NUS in Singapore. So today I would like to talk to you about this work on repulsion mixture models, which is joined with Maria De Iorio, Tim Wertz, and Alexander Morsen and Gregor, who are also connected, I see. And yes, it will be two works, actually. The first one that was originated with Maria and Tim, and then a second part where also Alexander and Gregor joined in this collaboration. So just to put the context, although with this audience probably is not really so needed, we're talking about clustering in a BNP setting where we want to kind of estimate a partition to identify the subpopulations in our data. And so there are some trivial or common issues that can happen after we give an estimation or a partition of the data. For example, clusters that look like they are a bit overlapping, or singletons that might seem like they're out of place. But so in general, the interpretability is a bit hindered in sometimes in the classical scenario. So in the last decades or so, the idea of repulsive clustering has gained popularity and has been promoted quite a lot. So this is kind of the context of this work. So the problem is that the components of the clustering have kind of a low separation, and different components can actually be very similar. So there is a degree of redundancy that we would like to kind of take care of. And the main idea is to introduce a penalty on the components that are placed close together to facilitate interpretation and induce some sort of sparsity. So the problem in standard mixture models is that the non-sparse behavior is facilitated by the IID nature of the location of the atoms in the mixture, because on their support, they are kind of freely moving with respect to each other. So what we need is some atoms that are mutually repellent to each other. So just to give a bit of notation, the model we're working with is a mixture model with a random number of components. So the data are distributed according to a mixture with standard Dirichlet weights, and locations that are in a standard mixture model would be IID, and then there is a prior on the number of components. Previous work to induce repulsion and therefore dependency among the locations include the determinantal point process, where the locations are not IID anymore, but they are jointly distributed according to joint law that is proportional to the determinant of a continuous covariance kernel function. So the idea is that since the determinant is proportional to the volume spanned by the data, ideally, then higher determinant means that we are promoting locations that are farther apart, so they are spread out in the space. And we have examples of the use of determinantal point processes in mixture model in Bayesian inference in the recent years. Another quite popular approach is that of repulsive potential. So the joint distribution of the location now is proportional to two components, one that is looking like a standard PDF, so it's a kind of a location-specific component, and then something that is function of pairs of the location. So this is usually called a potential or pairwise potential, because we're only considering two components at a time. And the inspiration for this work finds its roots in statistical mechanics, and we will see why where this comes from, kind of in a way. Again, there are examples in Bayesian statistics, and here I'm just showing you three scatter plots of samples from an independent bivariate scenario, a determinantal point process, and a repulsive potential example, and you see that the type of spread out kind of induced on the data is, or on the location in this case, is a bit different in the two scenarios here. So why do we want statistical mechanics? Well, the statistical mechanics is used to model interacting particles at equilibrium. And for example, for a given state of the system, for example, energy of a system, there can be different configurations corresponding to the same level of energy or state of the system we are interested in. So this is where the probabilistic part of statistical mechanics come in. And the repulsion comes in to model certain physical properties. For example, in models for magnetism, like the Ising model, the particles can take different spins, and if the spins are the same, then there is a repulsion component. Or with Coulomb gases, the particles of the same charge tend to repel by the Coulomb force, and also some other example, for example, involving chemical potentials can be considered in this scenario. What is done in statistical mechanics, to put it a bit in a simple way, is to resort to Gibbs point processes. So we usually define a joint distribution for the particles, starting from a function h called the Hamiltonian, which is a sum of higher order interaction potentials. So this is all the possible ways that the particle can interact. So h particle, where h goes from 1 to n. Then the expression of the Hamiltonian is usually exponentiated and standardized, and this would give you a joint finite multivariate distribution for the particles. And the normalizing constant called partition function plays a special role in statistical mechanics. What is actually done in practice is not to look at every possible order of interaction, but to look at pairwise potential. This is due to some standard approximations, but also to some problems that originate in physics. So these are much more tractable when we only consider two particles at a time. So why is the partition function so important? Well, in physics and in statistical mechanics, the partition function, as a function of this parameter zeta, gives you information about most of the thermodynamic properties of the system. So you can use this function to calculate the entropy or the specific heat or the pressure of the system of particles you want to study. And the parameter zeta, positive parameter zeta, controls the intensity of the repulsive forces in the locations, is often called inverse temperature because in the physics system that would be the unit of measure that is associated with this parameter. But clearly, if we want to use these joint distributions in statistics, then this is a normalizing constant of a joint distribution. So clearly it's important for several reasons. We would like to know it so we avoid double intractability in the joint distribution that we want to define. And also this might help us to perform posterior inference on the repulsion parameter zeta. So there are some connections with previous work. So Petralia, Su and Kinlande have proposed pairwise potentials in repulsive mixtures. So their joint distribution of the locations is proportional to an independent part, where G could be a PDF or a kernel of a standard PDF, and then a pairwise potential that is function of the distance or some norm between the two locations. The type of potential, so the function of this distance between the pairs, is different in the different works, but they all have roots in statistical mechanics or in physics. So the first two potentials here are reported in the same paper by Tanamura, if I'm correct, but they are actually originated from studies of subatomic particles or special gas. The second one is used to model the dynamic of argon gas, and in the first paper that was the word that was used. The third one is called Strauss potential or hardcore potential. So the interpretation here is that for two particles, if they are at a distance smaller than sigma, then there is an infinite amount of repulsion. But if they are beyond the radius sigma, then the repulsion is zero. So this is describing two physical spheres that cannot intersect beyond the radius, right? So they're just going to be like hitting each other and they cannot go farther than that. So this has been used also to model systems of physical spheres and not just particles like before. So anyway, a lot of inspirations from physics and statistical mechanics in the previous work. Let's see. No, okay. So now we would like to use these joint distributions to in our previous model, right? So we take a step back, we look at our mixture model with random number of components, and we say, okay, let's take this joint distribution and, for example, the repulsive potential distribution, one of the previous ones, and let's try to see if we can use it in this mixture model. So given the fact that we have the prior on the number of components, we would like to ensure that an infinite dimensional object exists so that we can perform inference for any m, basically. So we could use a limit-based approach, so a kind of Kolmogorov extension approach. So we take the finite dimensional laws and we assume that these are finite dimensional marginals of an infinite dimensional object that we want to prove the existence of. Then we check for the consistency of this finite dimensional object, and then we apply the system, the theorem of Kolmogorov extension. Unfortunately, we are already stuck at the consistency part because it's easy to see from the expressions before that if we start from a system with m+1 particles and we marginalize 1, we don't recover the same type of expression for the finite dimensional with m particles. So this does not allow for transdimensional moves in a standard sense, for example, in an algorithm where we want to infer the value m, and also does not allow us to make inference on the repulsion parameter zeta, which is in the partition function z. So what we can do and what we have done in this work is look at other results for infinite dimensional objects that can help our case. So what we're looking at is the theory of Gibbs measure, where the Gibbs measure are also infinite dimensional objects, but the consistency is a different type of consistency. What we are looking for is called DLR consistency, from the names of the mathematicians who came up with it, Dobryshin, Lansford, and Well. So they were motivated again by problems in physics, which is that of phase transitions and coexistence of phases. And they also had to prove the existence of an infinite dimensional object for certain systems. So the idea is not to work with marginals and finite dimensional distributions and then take the limit, but start with an infinite dimensional system and then look at the finite dimensional distributions as conditional distribution given the rest of the system, which is similar to looking at a finite number of particles and floating in some sort of medium or some sort of space, which is where actually the physics comes in and the application comes in. Unfortunately, this type of consistency does not guarantee existence and also not uniqueness. So we need some additional properties to ensure existence and uniqueness of this Gibbs measure. So what is done, one of the ways to do it is to resort to the large deviation principle. So the large deviation principle is a framework of study of the tail behavior of Gibbs distribution. So if we take a finite dimensional PM constructed like before, so starting from a Hamiltonian and then exponentiating and normalizing, then we take this in the log scale and scale it by a sequence of positive constants, then this limit will give you a function. And this function is called a rate function. It's a function over the space of measures. And this can be used to prove existence and uniqueness. So it can be shown that the infinite dimensional distributions or the Gibbs measure that satisfy the DLR conditions, so the consistency before, are zeros of this function, of the rate function. And on top of that, if it can be shown that the set of zeros is a singleton, then you have the uniqueness of the infinite dimensional measure. So this has been done for some of the distributions that we will see today. We have added a result on one specific case. This is the part of the theory that is connected to the concept of chaos in statistical mechanics, which is a rather complicated concept, but ideally is sort of an asymptotic independence in the scenario that we're working with. So still conditionally on all the system of particles, then asymptotically you have some sort of factorization of the joint law of the particles you're looking at. Okay, so the hard part, let's say, that is done. Now we know that there are some laws for which we can guarantee existence and uniqueness of the infinite dimensional measure. So which ones can be actually tractable? So let's give some examples. So we resorted to the description of gases through Coulomb law. So if you want to start with the Hamiltonian for the Coulomb gases for the univariate potential, it looks like this. So given a number of particles or component m and a repulsion parameter zeta, then the particle specific term is still in log scale, some expression that we will see later what it looks like. But most importantly, the pairwise potential is always the absolute value of the difference in log scale. There is a link between the Coulomb gases and random matrix theory that looks like kind of a jump right now, but is actually what is going to allow us to study this joint distribution more closely. So it is known that Coulomb gases and the law of this particle that behave according to Coulomb's law have an intimate link with the random matrix theory, and especially the joint distribution of the eigenvalues of the random matrices. So let's start with an example, with a Gaussian example. So a Gaussian random matrix, we take a matrix, then we populate it with standard random variables, and we symmetrize it. Then the joint distribution of the eigenvalues has this form. So the matrix is of dimension m, so we have m different eigenvalues, and we can see that there is a kernel part that is basically the PDF of the standard normal, and then we have the pairwise potential. So we have the product over all possible pairs of particles of the absolute value of the differences, which is exactly the same expression that we had in the Coulomb law for the gases. It can also be shown that this can be generalized for a general repulsion parameter zeta, positive parameter, and the joint distribution of the eigenvalues still preserves a similar form, where now the repulsion goes to the exponent of the differences of the pairwise differences of the particles. This is a contrplot of a bivariate example. You can see when the repulsion increases, we have that the components are more spread out and more peaked in farther apart. So the also very important case, a very tractable part of this distribution is that the normalizing constant is known. So this would change things because we can actually do more things when the normalizing constant is known. We didn't stop at the Gaussian. We also worked with the joint eigenvalue distribution for the Wishart and the beta random matrix. The Wishart as an additional scale parameter alpha. Here we see how the distribution varies for increasing alpha. So every kind of short movie is for alpha increasing, and the repulsion is fixed. And beta has two more parameters, right? So it's like a scale and rate parameters, and they also affect the distribution of the parameters. But they all have in common the fact that along the diagonal, clearly the density is zero, right? Because we are looking at the pairwise differences term additionally to the kernel of the density. Okay, so the law of Coulomb gases seems to be a good choice. So the eigenvalue distributions, they have good properties. DLR and LDP are satisfied. So existence and uniqueness of the infinite dimensional objects are guaranteed. So this means that we can use it in the BNP mixture model with random number of components, as we said before. Algorithmically, this is highly tractable. We devised a burden depth algorithm. So at every step, we propose to add or remove a component, and this leads to kind of straightforward calculations. It's not very complicated. And this is also thanks to the fact that we know the normalizing constant in closed form. So we also can do posterior inference on the repulsion parameter, which is usually not available when repulsive mixtures are considered. So in the rest of the work, I will refer to these distributions as Gaussian, Wishart, beta, Coulomb. But sometimes also with the name of the matrix ensemble they are referring to, which is Hermite, Laguerre, or Jacobi, where a matrix ensemble is a collection of random matrices that have the same distribution but varying dimension. And it will be even more clear in a bit why these names come up in association with these distributions. Some connections with the previous approaches. So the repulsive prior approach, so the ones that we saw at the beginning, where there is an independent part and the part that depends on the norm of the differences, can also seen as factorizing into terms. So we also have the same. So we also have psi1 and psi2, so the independent term and the pairwise term. But the repulsion part grows much slower than the other potentials that have been proposed before, especially close to the origin. So this is also related to the tractability of the Coulomb priors. And also the repulsion parameter is usually shared by the two components, psi1 and psi2. So we have that this information is also in the independent part. Other connections with other point processes. So in the determinantal point processes, this can be seen as a subclass of Gibbs point processes. And they were first introduced actually in 1975 to model fermion processes. So these are systems of fermions, which are also subatomic particles. So it was also used to model some particles in some physical systems because they naturally present an anti-bunching effect. So the fermions are observed to be repulsive. So the terminantal point process was a good start to model this type of particles. But more interestingly, the Coulomb distributions of the eigenvalues when zeta is equal to 2 can be expressed as determinant of some special matrices. So in particular, the pairwise differences of the absolute value of the pairwise difference is actually the determinant of the Van der Mon matrix. So it's a special matrix. So this is where this comes from. And the kernel part, so the positive definite matrix for which you would take the determinant to get the joint distribution of the eigenvalues, are actually constructed with orthogonal polynomials that are the Hermite, Laguerre, and Jacobi polynomial, right? So it's all kind of connected in this beautiful world of random matrix theory that we found out when we started working on this, and I think it's really fascinating. There's another connection that's very recent. So there's a general class of point processes that has been proposed recently by Beraha and co-authors. They propose a unified framework for random probability measures with interacting atoms. So their constructions is very general, includes a specific types Gibbs point processes and determinantal point processes, but at least as far as I could understand, the paper is quite involved. There is a struggle with tractability. So since the Coulomb priors are a special case of the Gibbs point processes, maybe I wonder if this can be used as a tractable example, maybe in that instance. So it's that's kind of an interesting question that I thought about when I was reading the paper. So back to the model. How do we put them in the model now? This is a hierarchical representation of the mixture model. So again, the data modeled with a standard mixture, but the locations are now with a Coulomb prior. So there's a joint distribution here that we can specify. The weights are constructed following the normalized independent finite point process by Argento and De Iorio. In particular, there is an R package called Antman that fits their model. It's very, very efficient. And we will use it as a benchmark to compare our model with the scenario, with the same scenario, but without repulsion, basically. Before seeing an example of application, a bit more on these prior distributions, there are expressions for moments available in closed form, which is quite nice, although they don't always look very nice. So, for example, the expectations for the Hermite ensemble is not available in closed form. And then the moments for the Jacobi case are quite involved, and they involve other moments, higher moments, but still manageable. And clearly they all depend on the parameters, the repulsion parameters, but also on the number of components. So this is quite interesting. So one way that these moments can be used is that you can use maybe a moment matching kind of strategy and to identify the parameters. And in some examples, we have actually used a symbolic solver to find like alpha, beta, and zeta here, so that we can match the parameters and see what happens. Some example of this of what happens with the moment. So in the Gaussian case, we said the expectation doesn't exist. So this is the mean of a two-component prior for increasing value of the repulsion. You can see that there is a high level of symmetry in the two around 0, which is also similar to what we saw in the contour plot for the bivariate. So we had like these two modes that were kind of going farther apart. For the Laguerre ensemble, there is an additional parameter. So these are mean, variance, and covariance as a function of the repulsion parameter and the scale parameter. There is an additional constraint that the scale parameter has to be bigger of -2 over zeta. So you see here in the region of the plot, there is some parts that are not acceptable values for these parameters. And for the beta case, there is a high level of nonlinearity in the variance and the covariance as a function of alpha and beta. So this is for zeta equal to 0.1. And for zeta equal to 1, we still see quite a high level of this nonlinearity. Okay, so this was for the moments, but one quick example. So we use a benchmark data set to try and see how this prior works. We use the air quality data set. It's a bivariate data set of solar radiation and ozone measurement in New York. And so we fit for our model, we use a Gaussian Coulomb prior for each dimension of the data, right? Because the Coulomb distribution that we are defining are for univariate cases. So it's for joint locations, but the locations are univariate. So for each dimension of this data, we use a Gaussian one with a different repulsion parameter for which we put a gamma prior. The clustering here that you see in the plots with different colors is computed by minimizing Binder loss function, and the independent model in the first panel is computed with the package Antman. So we see that in terms of clustering, there is a coarser partition when we include different type of repulsion. The first one is with no repulsion. The second one is the repulsion by Killand and co-authors, and the third one is our Coulomb prior with the Gaussian from the Gaussian ensemble. So our proposal has a coarser partition, only finds 2 clusters, and also works quite well in terms of density estimation, looking at the contour plot here. We also explored different choice of eigenvalue distributions for the same example. So the locations for the ozone data set are real. So in the Gaussian case, we just plug in the eigenvalue distribution. For the Wishart and the beta case, we have to do a transformation, so a log transformation or a logit transformation to go from one to the other. But we see that a posteriori, the number of clusters and the number of components are very robust to the choice of the eigenvalue distribution. While the posterior distributions for the repulsion parameter zeta is also quite similar in the 2 components, so there's kind of the same amount of repulsion needed. And but they do differ for the different priors, the eigenvalue priors that we use, and this is clearly because the role of the repulsion parameter in the different priors is slightly different due to their expression and the kernel that are used in the eigenvalue distributions. Okay, so this was the first part of the work where we explored repulsive priors mostly for location parameters. And then now the next step is, okay, what happens to the weight of the distribution? So we would like to work with repulsive weights, which are not this type of repulsive weights, but we are trying to understand how can we put some repulsive prior also on the weights of our mixture. So there have been examples before that allow repulsion on location on the weights, although usually the repulsion is on the location, especially in the recent work. But there is this example. I'm sure maybe there are some others, but I wanted to bring this to your attention. So Huken and co-authors propose a non-local priors where there is a possibility of repulsion on the weights, but still also their tractability is an issue, and especially the number of components was fixed. And it was chosen by model comparison techniques, looking at different goodness of fit measures. So the idea is to use the tractability, exploit the tractability of the Coulomb constructions and see how we can use it for the weights. So if we start with a vector of Wishart Coulomb random variables, right? So this is a joint distribution of the eigenvalues of an m-dimensional Wishart matrix, random matrix. And you can see there is a normalizing constant that is known in closed form, a kernel part that looks like a gamma distributed random variable, and then the pairwise potential that is function of gamma, where gamma is the repulsion here. So what we do, we go from here, like we would go from a vector of gammas to the Dirichlet, then we normalize a vector of Wishart joint distribution to obtain what we call the Dirichlet Coulomb distribution, which has this expression here. Again, the normalizing constant stays known. We have the kernel here that is the kernel of the Dirichlet, and then the repulsion, this time on the weights. So unfortunately, this was not completely new, although it seems quite a straightforward extension. It first appeared in 2009 in this paper by Pham Gia, and the name was Selberg-Dirichlet distribution, where Selberg refers to the Selberg integral, which is a very important integral in all this calculation. In particular, it is equal to the normalizing constant in the beta Coulomb distribution. So that's where the name Selbert comes from, in case you encounter it again. So the beta Coulomb distribution had a product of beta kernels in the kind of independent part, and the Dirichlet Coulomb distribution had a Dirichlet kernel. So this is kind of the similarity also. And the two distributions coincide for m equal to 2. This distribution was recently studied in a paper 2022. It's called Bivariate-Selbert beta type 1 distribution. And as we desire, when gamma is equal to 0, so there is no repulsion, then the standard Dirichlet distribution is recovered for these weights. So it can be used for a mixture model with random number of components. So we will have the tractability, and then the algorithm can still be based on the BERT-DET approach that we had for the locations. But now when we want to propose to add or to remove a components, clearly we are affecting the whole weights, so that we need to propose a new vector of weights in a clever way. And but the algorithm still works, and it mixes quite well, and is very tractable also in this scenario. So here I have an example of samples from this distribution with dimension 3. So this is a ternary plot, kind of a representation of the simplex. And we have no repulsion. So this is samples from the Dirichlet distribution for different values of alpha and beta. We see that, as we know, the alpha and beta values kind of are responsible for where the mass is on the simplex. And the red lines are the places where at least two of the components of the three-dimensional vector are the same. Okay, and we see that here the points are clearly bypassing all the lines. When we start putting a bit of repulsion, this is for the matching values of alpha and beta, but the repulsion is equal to 0.5, we start to see that the support is excluding these lines, because we know that in those places, the joint density of these eigenvalues or the joint density of this Dirichlet distribution is actually is equal to 0. So the points are clearly avoiding that place. And if we add even more repulsion, then we see that this effect is really clear. Now it will get to a more clear example. And also with the amount of repulsion, the points are also more spread out towards the border, because they're clearly avoiding the center where the components are the same. Okay, so we haven't studied a lot of properties of this joint distribution. This is still ongoing work, but I wanted to show you a little bit how they work with an application. So we're going to look at an application to the galaxy data, also another benchmark data set. Now we have two components to look at. There is the locations and the weights. So one question is how to choose the repulsion parameters, and then what is the effect of the combined location weight repulsion. So this is the inference on the galaxy data using a Gaussian Coulomb priors for the location only, and it's compared to the no repulsion case with Antman. So the pink line is a density estimation from Antman, and the other lines are density estimation with only repulsion on the location for increasing repulsion zeta. So what we see is that we increase repulsion, we have less variability in the number of clusters. So the blue with the repulsion equal to 5 is centered on 4. And the density estimation also is kind of improved when we increase the repulsion. When we put only repulsion on the weights, so we use a Dirichlet Coulomb prior for different values of gamma, also increasing values of the repulsion, and we compare it again with the no repulsion case of Antman, we see that this is a bit of the opposite. So we still have fewer clusters when we increase the repulsion, but the density estimation is not the same. So when we have less repulsion on the weights, we have kind of a better density estimation recovery, but when we increase the repulsion, there is kind of a smoothing effect that is not necessarily desirable, depending on the problem at hand. And also it looks like the coarseness of the partition, so the distribution of the number of clusters is really, really forced towards just a few components when the repulsion increases, much stronger than what it was happening with the locations. So let's see what happens when we put them together. So in these panels, we have each line is a different value of zeta, the repulsion on the locations, and each panel is a different value of gamma, increasing gamma for the repulsion on the weights. So in the first one, where the repulsion on the weights is still quite small, we see that the results are relatively satisfactory. Maybe when zeta is equal to 5 is the pink line, we are losing a little bit in goodness of density estimation in the small modes at the extremes of the histogram here. But as soon as we increase gamma, the repulsion on the weights, we are not doing so well. So this smoothing effect is really evident and is really strong. So it looks like these parameters need to kind of be controlled in some way. So the combined repulsion might lead to this over-smoothing, which might not be desirable. So the density estimation usually is favored by the repulsion on the location, but this effect is reduced when we increase gamma. So there might be some identifiability issues. Probably we're actually looking into this topic. This is one of the open questions that we have for this project. But for now, our approach is to try and look at constraining these parameters somehow. So we have 3 proposals. One is to fix the ratio of the two repulsion parameters to a constant. Either fix a product or in case of ratio of product, then we put a prior on gamma. And when the ratio or the product are fixed, then gamma is equal to 0.1, since we saw that it was working quite well in the previous example. And then we look at different values of the constant C. These are 4 panels. So gamma is in the first row is fixed to 0.1. And then we have either the ratio or the product. And we can see that in case of the ratio, things seems to be much more robust to different values of the ratio, while the product still suffers from that over-smoothing issues that we saw before, even when gamma is fixed to 0.1. When we put a prior, we have a similar behavior. There is a bit more variability in the ratio case, but we are quite satisfied by this result. Actually, it's very consistent with what we saw before, also in the case of the product. So yes, just to conclude, so we, in the previous part of the work where we kind of looked a bit more at the theory of this type of repulsion model, we tried to establish a connection between different repulsive approaches and also different theoretical frameworks. So we ended up exploring the Gibbs measures as a tool to extend the finite dimensional repulsive distribution that we wanted to work with into a mixture model with random number of components. And this led us to study the DLR consistency and large deviation principle theorems to ensure this existence and uniqueness. We found our favorite joint distribution in that of the Coulomb gases, and the relationship with the random matrix theories and the eigenvalues of random matrices was key to performing to construct a model and to perform this posterior inference. And in particular, now with the known normalizing constant, we can actually perform posterior inference on the repulsion parameters, which is something that usually is not available in this type of models. The second part of the work, which is still ongoing, is exploring repulsive weights. So how can we use them in the mixture models? And there are still some questions. So how to set this sort of competing repulsion between location and weights, and maybe study the identifiability of this model, and also how to tune it maybe with some information a priori. Yeah, so thank you for your attention, and I'm happy to take any questions.
Okay, thank you, Andrea. It was really interesting. Let's take questions if there's any. If you have questions, then okay.
Let's see.
Yes, Alexandra. Yes.
Hi, hello. Can you see me?
Yeah.
Can you hear me? Okay, because
Yes.
I don't see myself. Andrea, thank you very much for your talk. I enjoyed a lot. I have a few questions. I don't know if I have time enough. But the first one is more like a comment, because I'm actually wondering if repulsive weight is repulsive is the right words for the type of priors that you are actually assuming for your weights. I guess that it's difficult to define what does it means that weights are repulsive. Why this is clear to me, the definition of repulsive locations for a mixture model is a kind of easy and intuitive to define. So I'm wondering if repulsive attached to weights is the right word for the prior that you are indeed assuming. The other question, this is really a question that I'd like to ask you, is you were wondering something about the matching of the Z parameters, so where the Z, that they can assume different meanings according to the prior, to the model that you have selected. So I was wondering or suggesting if you can somehow compare the different priors using some other functions. I mean, there are functions, tools which indeed measure the repulsiveness of, well, I'm talking about point processes, of the point processes that you define. So I was only curious to know if you have thought to this idea of, using something more to compare the repulsion of your priors. And my last question is, actually, it's again a comment that you have in part already made, because what I want to say is that the prior on hyperparameters which control the repulsive behavior of our process, of our weights or our location, I'm sticking at the location, can be tricky because, as you said, there could be involved more parameters which somehow contrast each other. So we could select non-repulsive behavior without even knowing it, that we are actually not selecting repulsive behavior. But indeed, I guess that the your last slide, when you were discussing how to select somehow the hyperparameters, is something that is more convincing in my opinion. And that's all. Thank you.
Okay. Thank you. So the first one, the name, yes, we just went along with how we were calling the other parameters. So yeah, but I agree that maybe it's a bit more difficult to see. But even if it's a closed support, I think the weights are still like, if you have two components, one has to be very high, the other one very small, or if you have three, then there is one that is very high, and because you have the constraint that they need to sum to one, right? So there is maybe more that goes on than just repelling. But yes, maybe it's good to think about alternative names. Yes, although there is a sort of repulsion that happens also there. The second one about, comparing the amount of repulsion. Yeah, no, we only looked at these parameters, zeta or gamma in this presentation, and compare, for example, the posterior distribution of them. But thank you for the comment. I think maybe I will ask you more about this comparison that you have in mind. And then the last one, yes, it can happen. We have seen some examples of applications or also simulations where actually the posterior, if you put, I don't want to say a non-informative prior, but a prior that is standard, for example, we use a gamma 1,1, sometimes the posterior is concentrated on very small values of the repulsion parameters. So it's going towards, it's indicating maybe that the repulsion is not needed in that example. So that can happen as well. But we have also tried to constrain especially the gamma parameters, for example, to be on an interval away from zero. This is something that can be done also because the tractability is there. So different options can be explored quite easily in the same context. Yeah. I hope it answered partially at least your questions.
Yes, thank you. But we will discuss in the next few weeks, I guess.
Good. I have a question. It's a very nice talk, Andrea. So one place that mixtures come up a lot, or in when you have subset selection for variable selection, that's a very natural place. And unfortunately, I missed the beginning of your talk. I don't know if you you mentioned it, but to what extent have you thought about, using these repulsive models and assess them for variable selection types of problems with those kinds of mixtures?
Thank you. Thank you for the question. It's not part of this work, but it's something that has come up in discussions and how to use it because there was a lot of kind of background theory to put in order here. We focus more on giving examples that were benchmark in a way to just show how the behavior is and sort of if we can get some interpretation out of the result. But clearly, there is an open opportunity to see how these priors can work in practice in actually problems where you want to study maybe something more like real data or real life problems. Yes, and variable selection is definitely something that is very interesting in this sense, and it could probably help to distinguish the kind of important effect to the non-effect with a repulsion term. It could be very interesting. Yes.
Yeah, well, what's great is that you're kind of laying the foundations for that. And often people who have used these ideas in variable selection haven't gone back to really establish what's going on in the base case. So I think you're in great shape to sort of now begin to tackle those things. Thank you very much.
Great. Thank you.
Okay, Raffaele, go ahead.
Hey, hello, can you hear me? So it's a question a bit related to what the previous one. So I'm wondering if you can achieve with your approach different kind of behavior of the atom or of the weights, kind of instead of repulsion, attraction, or other kind of constraints or behavior that you want for the atoms, for instance. Is it possible, or you can just achieve repulsion?
Okay, so thank you for the question, which I should have mentioned that when I mentioned your paper, Beraha, those general framework can also accommodate attraction. So yes, I think in this special case, to get this level of tractability, the inverse temperature, or the zeta, has to be positive because it comes from a problem that is solvable under certain conditions that are from physics, and these are requiring this. So we have not studied the attraction part, but other repulsion potentials, or called repulsion potential, actually are just potentials that can attract, and but for which there is no normalizing constant. So we were, it's not so tractable as this one. Yes. Thank you.
Are there any questions? Okay, so then let's stop here. Oh, yeah. Okay, Matt. Sorry that I missed.
Sorry about that. Can you hear me okay?
Yeah.
Andrea, thank you so much for this talk. I was curious if you have pursued the Coulomb-Dirichlet in the sense of repulsion between compositional vectors instead of within compositional vectors.
Wait, help me understand. You mean?
So if you considered the atoms being Dirichlet distributed themselves, so say you're in a count data setting and your atoms are Dirichlet distributed.
No, we have not looked at that, but that's very interesting. Yes, I guess it can be used there. I mean, it's the support allows it, so yeah, it could be used. Thank you.
Thank you very much.
Okay. Any other questions? Last round. We still have time don't be shy if you have any questions. Okay, so then let's stop here. And thank you again, Andrea, for
thank you again.
talk. And as I said, beginning, we will resume our webinar this fall, and that as we line up the seminars, then you will announce. Okay, thank you so much for joining us. Okay,
bye.
Thank you. Bye.
Thank you, Andrea.